So today we'll finish up talking about steel, and we'll talk about a couple of things, both different types of steel, so what we mean by our architectural steel, when steel is exposed to view, what we have to do in terms of preparation and things for that. We'll also talk a little bit about fabrication and about detailing, and in particular about bolting steel versus welding steel, and how we put the pieces that come out of the mill together, both in the shop and on the job site. Steel has a lot going for it in terms of its performance and in terms of its flexibility in design situations. The one thing that is maybe working against it as a material is that it is very costly. And that cost comes really from three places. One, it is difficult to manufacture. We've got to get iron ore. We have to get coal. We have to have these incredibly high technology furnaces, these very high energy furnaces to actually make the molten steel. We then need very specialized equipment, large factories to produce steel in the shapes that we're used to having. Then we need to take that steel and we need to do things to it to make it useful on a job site. So whereas with concrete, we're basically bringing raw material to the site, pouring it into forms, and being done with it. Steel, we have this added step, usually in a steel mill or a steel fabrication shop, where we'll actually drill and cut, splice, do things to it that mean that when we get it to the job site, we're just basically bolting or welding it together. And all of that prep work takes time. Also takes very specialized machines and specialized labor. Once it's on the job site, we're using relatively small, relatively lightweight elements, so they're easy to transport, they're easy to move into place. But then we also need specialized labor to actually assemble the pieces. Iron workers have to do the bolting, or if there's on-site welding, we need special welders to do that as well. So there's a lot of preparation and also some specialized assembly that goes on the job site, in addition to the material costs. And with steel, we have about a third of the cost being material, a third being fabrication, and a third being the actual assembly, right? Three places where we're spending money to get this very, very high performance that we're used to out of the material. That gets even greater, the costs get even greater if we go to what's called architecturally exposed structural steel. So if we're burying the steel in concrete, or if we're burying it in gypsum, or if we're hiding it somehow, we don't have this extra set of steps where we're making the steel kind of visually attractive. We can have connections that are a little bit rougher. We can have surfaces that maybe don't align quite as well, or are not quite as polished as we do when we specify what's called architecturally exposed steel. When we do this, we're taking basically an industrial material, a material that is precise but maybe not consistent in its color or in its texture. We're putting that into places where we really are demanding precision, and we're demanding very, very consistent surfaces, colors, things like this. So if we want to expose the steelwork in a building, which we very often do because we like to see the actual structure at work, then we have an additional set of standards, tighter tolerances, tighter production standards, assembly processes that are often much more difficult because we like to hide things like bolts and welds. And we have an additional cost then for all of the sort of finishes, all the sort of polishes basically that make steel an attractive architectural element in addition to being a good structural element. We have a couple of ways that we deal with this. We can mitigate the costs somewhat if we're careful about some of the processes and some of the material aspects that we choose. So looking at the kind of architectural input, one of the big things we can do to save costs when we're designing architectural steel is to think about how the assembly process works and to think about what's easy to do in the shop versus what's easy to do on the job site. And the number one example of this is bolting versus welding. If you think about this, when we have a piece that comes to the job site, it's all usually going to be put in place up in the air, attached to a couple of columns or something that are maybe a little bit flimsy, hard to reach, and not necessarily very stable. Okay, now imagine who you want up there putting it together and what processes you're comfortable with them using. Someone who is just bolting two pieces of steel together has a relatively simple task with a relatively simple set of movements. Someone who's welding those together has to basically have 360-degree access to that joint. So very commonly, one of the first things we'll think about when we're detailing steel, especially when we're detailing architectural steel, is can we do all of the welding that this connection involves in the shop under controlled conditions? And can we do most of the bolting, the very simple stuff, on the job site where it's relatively challenging to get any sort of finesse or any sort of difficult maneuvering around a joint done? We'll also look at how complicated the shapes we want to use are. If we're using architectural steel, very often we'll prefer to have hollow tube sections instead of something like a W shape. If this is the case, then we need to think very carefully about how those go together, how we access connections in a tube or in a closed section. If we're thinking about connections that are overly complicated, we might want to think about ways to either simplify those or to break them down. So again, we can do a lot of the work under controlled conditions in the site. And we might think too about the size of things that we can bring to the job site. Remember, everything that comes out of a mill and comes to a construction site has to fit on the back of a truck typically. So we're limited in the scale of things we can bring to the site, and we can be clever about sort of sizing the articulation of the steel structure so that we're using pieces that naturally fit on highways, right, or onto cranes. And then we'll look also at finishes and durability. If, just like in concrete, if we want a sort of raw steel finish or a galvanized steel finish or something, that may be difficult to maintain on the site. If we're painting the steel after it's in place, a lot of times this can hide some of the mistakes or scratches or imperfections that may happen when we're assembling things. So we may think carefully about finishes that are a little bit more forgiving when we're exposing the steel architecturally. And then finally, there'll be a discussion about tolerances. It's very easy to get very, very high tolerances or tight tolerances, again, in factory conditions. It's a little bit harder to do that in the chaos of a job site. So anytime we want to be really precise with steel, we want to make sure that we're taking care of that in the controlled conditions of a fabrication shop, and that we're allowing for some of the imperfections, some of the chaos that naturally happens on a job site. A typical fabrication shop takes raw steel out of the mill, so rolled sections, and then applies other pieces to it or drills or cuts it so that when it comes to the site, it can be assembled very, very quickly, right? It's like kind of taking raw pieces of wood and adding all the stuff to them that make a flat pack. If you're assembling furniture, you don't want to have to do all the drilling and stuff in your living room. You'd like that to all happen in the factory. When it gets to you, you'd like to just have a few simple operations that put it together. And the fabrication shop is where this typically happens. So upper left, you see raw steel coming into the shop. Lower left down here is a welder. He's welding what looks like an angle onto a W shape. That angle has already been drilled. Here's another example up here. So you can see those holes are where bolts are going to connect this probably girder to a column. And you can see this is what we call a shop weld around the base. So that welder has had very, very easy access to all four sides of the angle. And before the angle gets put on, it's been drilled very precisely on a drill press. And those holes are exactly where another piece, the column piece, has similar holes drilled so that the bolts will fit right through. A lot of coordination, a lot of very, very fussy, sort of precision-oriented cutting and slicing, but because it's in a factory, because it's in controlled conditions, this is okay. We can achieve those. Here you see sort of mass-produced angles. This is a very, very common thing to see, angles with holes drilled in them for bolts that will get welded onto a steel W shape. And here another very common detail, these are going to be columns. And these are thick base plates that will spread the load of that column over probably a concrete foundation. And here you see holes drilled in that very thick base plate that will allow bolts in the foundation, or maybe a bolts coming out of an anchor plate on the foundation. Those will be aligned very precisely, and those, as you can see, will make sure that the column is placed exactly right. And then here are finished pieces. You can see some familiar shapes. Here's a W shape for sure. Angles that will attach it to the column. This angle along here is probably there to accept a piece of cladding or something once the girder is in place. And you'll see very typically a lot of basically record keeping. Chalk marks on the steel that explain very precisely where this piece is going, sometimes what pieces it has to connect to, so that there's no delay caused by accidentally putting the wrong column in the wrong place. Right? It does happen. Obviously, that's time and money that could be spent elsewhere. And so the fabrication shop will go a long way to trying to make sure that these pieces, once they're formed, are very accurately cataloged, triple checked to make sure that they're going to fit with the piece that they're going to conjoin with. Once those pieces are all fabricated, remember they have to get put on a truck, so there are limitations to certainly the length of steel pieces that we can use. Depending on how much room we have on the construction site, they may get shipped out and sit there for a while, so they may have to have some kind of corrosion control if we're expecting them to be outside for a period of time. They'll get picked up typically by cranes. One of the great advantages to steel is that it's lightweight, relatively lightweight. So we can use sort of smaller cranes than we might for precast or something like that to lift these pieces into place. And here you can see, here's a column on a hook. This is a detail that we'll talk about in a minute called a column splice, where those two plates will connect this lower column with the column on top. More job site photos. One of the things that we don't think about so much, but that is a big issue with contractors, is because the steel is so precisely cut, it has to be put in really exactly the right place. And as you can imagine, the methods that we have to move the steel around are not necessarily as precise as we'd like. So there's a lot of work that goes on not only with iron workers actually bolting things together, but very typically in a steel operation, you'll have a whole team of surveyors on site that are making sure that the steel ends up in the right place and that we don't start building up errors in the location of things because small things get misaligned. The precision that we rely on, the precision that steel is good for, comes with the cost of having to make sure that we are putting stuff in exactly the right place. And you'll see surveyors tools, and again, this kind of in-place record keeping happening to make sure that the right pieces are getting put together in the right way, and especially in the right place. And tolerances, again, remember with steel can be as tight as a 1/16 of an inch. That's great in terms of being able to detail very sharply. It is a problem on the job site in trying to keep those kinds of tolerances, again, in conditions that are often very messy, very chaotic. Here you see a couple of sort of transitional pieces. Very often we're taking the steel and we're putting it onto a concrete foundation, right? Typically we're putting it on a concrete foundation. And remember, concrete we don't think of as a particularly accurate material. So we need to have ways to get a very precise, tightly detailed system of steel construction onto a foundation system that maybe a little bit not quite where we had anticipated it. So here you can see anchor plates that are basically making that transition from concrete to steel. Very often they'll be grouted. So here you can see that these plates sit on top of and within a bed of lightweight concrete that ensures that they're level and allows us to shim them up and down a little bit. And those plates also usually will detail the top of the foundation so that we have room to move the anchor plate around a little bit, right? Using surveying to make sure that the anchor plate gets in the right place so that the column above will be in the right place. We can shim columns on top of that. Sometimes we'll have slotted connections in steel plates so that we can move them in two directions, and make sure that so long as we can shim it up and down, we still have a little bit of room to move in the X and Y direction to take up the tolerance that we naturally get in concrete and to transition to the very precise location that we need for the steel structure to come together. As this goes up, the steel structure needs to be designed not only for stability once it's finished, but it has to be stable as it's coming together. And very often, an incomplete steel structure, something without its lateral bracing in place yet, is going to be relatively flimsy. That's fine. It's not taking the loads that it will once it's fully occupied. But nevertheless, we have people walking around, iron workers especially, who are very often tightening bolts, making welds, moving some of their equipment around. We need to have a stable structure for them to work on. So very often you will see kind of temporary lateral bracing. This is fairly crude cross bracing going on here. You can see it here as well. That structure is going to move a lot, but those cables are going to prevent it from moving too much or from deflecting too much. Here at the top, you see this is a steel column that sticks up above the floor, and these two plates again are going to form the connection to the next column or the next piece of column that goes on top of it. We have to, as we're detailing steel, anticipate how these things are going to come to the site, how they're going to come together. And while it may seem natural to put a column splice at the floor level, here what we're doing is a good principle of steel detailing where we're sort of spreading out the connections. So we're not bringing a whole bunch of pieces, 7 or 8 pieces of steel together at one point, but we're letting some pieces continue, framing other pieces into it, and trying to limit the number of cuts, the number of bolts that we're making in one place. You can see that where girders and beams come into a column, we have a little bit of a steel traffic jam, right? A lot of bolts, and remember, each one of those bolts needs space around it for someone with a wrench to tighten it. So all of these connections coming together here mean that the steel detailers in this case have been smart, and they've made the connection between columns up 3 or 4 feet usually above the floor level to try to reduce some of the chaos that happens around these floor and column connections. Here close up, here's a column splice where you can see again we've had the bolted connections, angles welded to the beams and girders, brought out to the site and bolted through holes that are cut in the shop, both in the angle and in the column. And then here you can see these plates on the top that are going to accept the next piece of the column that comes down and transfer those loads into the lower piece. Again, good practice to try to separate as much as we can so that there's plenty of room to work around all of these bolted connections. And two, this helps make the building stabler in the long run also. A column splice is almost always going to be weaker than the column itself because we're basically taking a couple of disconnected plates, asking them to do the work of a W shape or compact section. If we do that right at the floor, we have, of course, the longest possible span for the column, and we're putting a weak link right where we're asking the column to accept more loading, sometimes loading that's not just vertical, but maybe lateral as well. If we move the splice up, we're making it easier to construct, and we're also, as you can see, making it a little bit sturdier, right? By making the floors now frame into a more or less continuous column instead of breaking the column right where it's going to be accepting things like lateral loads. When we're detailing steel, we're trying to think not only about what the finished connection is, but also, again, how people are going to actually put these together. And so we'll have a number of sort of typical details that both help with the finished performance, but also acknowledge the fact that human beings have got to get in there with wrenches or machines and actually tighten things like bolts. So here's some kind of standard details. You can see here we have a beam coming into a column. And this is going to be a moment connection, so we're trying to ask the beam and column connection to be monolithic, right? To be a moment connection. And what we worry about is the kind of fragility of steel, right? Again, because we're working with such thin steel pieces, it's a relatively hard thing to do to ask a beam and a girder to take a moment connection, or a beam and a column. So here you can see a couple of pieces, some of which we'll put in place in the fabrication shop, some of which we'll put in place on the job site, that help us to make a really rigid steel connection. The first of these are plates that are welded into the web depth of the column. So here's a compact section, and you can see that these continuity plates make what we call a torque box, right? This is a solid box of steel that basically ensures that any bending force that goes into the column is going to get transmitted throughout the entire column, and we're not just going to be stressing one flange or the other. Here, this is what's called a shear tab. The engineers are relying on this to take most of the vertical load, right? So exactly what it says, transferring that shear, which is highest at the end of the beam, directly into the column. And you can see here too that we are welding in place. These welds here are designed to transfer the bending moment in the beam into the continuity plate and into the column. So even though we try to limit the amount of welding on site, if we're trying to get moment connections into a steel structure, we are going to have to do some welding to ensure continuity, right? To make it into as monolithic a structure as we can. And you can see too that we have some details that allow for things like continuous welds. So here, this is what we call a coped beam. They've taken out a little corner of the web, and that allows a welder to get in there and to actually make a continuous weld all the way across the interface between that beam and that column. And here you can see some other coped beams here. These beams are coped to get around the flange of a girder that they're going to be framed into. So you can see that we want to get that beam all the way into the web of the girder, but to do that and to maintain a consistent floor level, basically, between the two flanges, we have to take a little piece of the beam out, right? Otherwise, the flanges get in each other's way. We can't get the beam to get all the way to the web of the girder. And we're always trying to do that. We're always trying to frame in as tightly as we can, as close to the center of gravity of a steel member as we can. So it's important to do this kind of fabrication, and what this does is it lets us sort of stick this like snoot of steel into the depth of the girder, and to provide a very, very robust bolted connection right from web to web, which is the way that the connection is going to be strongest. And here in action, you can see coped beams, just like what we just looked at here. Notice here that the angle is welded to the girder in this case, bolted to the beam. So that angle will be in place when we put the beam in, and it gives us something basically to rest the beam against to ensure that it's in the right place. And we'll think that through. We'll think through the sequence of where we want pieces welded versus where we want them bolted. And we want them welded to the pieces usually that are earliest in the sequence. Here you see an open web truss that's being bolted to a girder. And here, because we have a bearing plate on the truss, all we're really doing is putting in a couple of bolts to make sure that the truss stays in one place. We're not actually taking shear through the bolted connection. The shear is actually going right through the bearing plate here itself. And then here are a couple of more slightly complex connections. Here we've welded a plate to this beam. For some reason there needs to be a difference in height between the top of that flange and the top of that flange. And so in the shop, that plate has gotten welded to the web of this beam. That's been bolted to welded to the web of this beam. And then you can see that it has an angle connection here that's then bolted into the girder itself. And here you see a close-up of what those connections look like, right? Nuts and bolts just like we would get from a hardware store for wood construction, but here made of usually stronger steel and designed to take those much higher loads that we'll get in a multi-story structure. When we're welding and bolting, we have a whole sort of family of details and of ways of communicating what's needed. Usually these will be done by structural engineers, but we'll be looking at these often because we're sometimes going to be concerned with how large the bolts are. If they're exposed, we're certainly going to be interested in what they look like, but we may be coordinating things like mechanical systems or finishes that require us to know how much room we actually have around a steel element. So here you can see standard bolt diameters, and you can see too that we have a whole set of dimensions that have to do not so much with the bolts themselves as with the dimensions that we need to get a wrench around that bolt, and of course a human hand, a human wrist to connect these. So we're limited in terms of where we can put the bolts, both structurally. We like to put them on the center lines of steel elements, but we also need space around the bolt to get that wrench in there, and particularly to get a worker's hand to be able to tighten that bolt. Sometimes these are done mechanically. We may need more or less space to get a mechanical wrench around that. But as you can see, this means that we need more space sometimes around a connection than we might at first think. If we've welded that angle to one of those pieces, then obviously we can limit the amount of space we need around a bolt to one axis instead of two. But you can imagine too that when we have two bolts here, we have to think about how those are tightened in not just one direction, but clearly in both. And this gets particularly complex when we start dealing with difficult geometries, because we have to think not only about what those steel elements are like, how much space they have when they all come together, but we also have to think about the kind of work cloud around it and how we get people in to tighten all of those bolts in all of those different directions. As you can see in this case, we have some pretty tight areas that result from the acute angles in the geometry of this roof structure. Right? Just a little bit tricky to get in there and tighten those last bolts. And this is important, of course, because bolts have to get tightened to a certain level for the structural connection to be functional. And also, they have to get tightened in a way that they will be locked, and that the typical vibration that happens in a building won't eventually loosen those. So the construction conditions on site can, in fact, affect the structural performance of a steel structure going forward. Here are a couple shots of what steel construction looks like sort of close up as things are being assembled. You can see sometimes access gets a little difficult, right? This iron worker is going to have difficulty seeing what he's doing. He's, of course, proceeding more or less by feel because that bolt is underneath the flanges there. Here's what the bolts look like, locking washers. Here's the nut, here's the bolt. And you can see here two examples where an iron worker is using a mechanical wrench to actually tighten the nuts on these bolts here. And you can see too, pretty precarious position, right? This is, iron workers have a particularly dangerous job. They're on these small bits of steel, and they're very often using tools that have a great deal of torque with them. So there are safety concerns in addition to construction and access concerns. And the more that, the easier basically we make it for these workers to access these connections, usually the better quality, of course, we can expect, right? The more time and attention gets put on making sure that the bolts are in place correctly. When we're welding elements together, engineers will get particularly concerned with both how much welding material there is and also what kind of shape that is, whether they're welding two flat pieces together or two planar pieces together, and whether those pieces are prepared in any way. So whether they're sliced in a way that provides for more surface connection between one and the other. A weld works basically like an adhesive, so the more surface area we can weld between two pieces, generally the better. And as you can see, there's an entire vocabulary of different types of welds and different kind of ways of enhancing those welds that will very often get specified depending on how much structural work a connection has to do. We don't typically worry about these unless they are architecturally exposed, in which case we'll have a set of specifications that talks not only about the size of the weld, but also anything that has to be done to it afterwards. So in particular, whether welds have to be ground smooth so that we're not seeing discontinuities in surfaces between the weld itself and the steel surrounding it. And you can see steel connections can get really big. When we're doing bridge work, you can imagine the amount of access and the amount of difficulty there is in getting to some of these locations that are either really high up or very remote from places that are easy to access. So here you can see this is a crew of iron workers that's bolting. And as you can see, they've got a big task here. They're finishing up a big task. And this is a pretty precarious position for someone to be working in. Much easier when we can to prepare those kind of connections in the shop, to weld them in the shop and then to just bolt them in the field. You can imagine how much more difficult this would be if this was a welder instead of someone just bolting. And they've got an incredibly hot but a machine that has to be deployed with incredible precision in those kind of conditions. And at the other end of a steel structure, we talked about sort of going from concrete to steel at the foundations. And we'll also typically go from steel these days to concrete in the floors themselves. So we talked a little bit about steel decking when we talked about pouring concrete. And here you can see job site photos of that steel decking being laid out. And this is like the sort of last bit of the steel system and its interface with the concrete system. We talked, when we talked about concrete, about the fact that we usually lay these in corrugated decks. This is a rolled steel material that's very easy to fabricate and therefore relatively inexpensive. And as you can see, it creates these kind of miniature T-beams once concrete gets poured into them. Very often, to take advantage of the fact that the steel deck is going to be on the bottom, where we typically expect a lot of tensile stress in a simply supported deck. Concrete's going to be on the top. So we'd like those to work together, and to prevent the two from slipping past one another, from shearing past one another, very often we'll specify what's called a composite deck, where we're actually welding studs to the steel decking, or in this case to a set of beams and girders. And those studs, once concrete gets poured around them, will form a mechanical connection, or what's called a shear bolt, between the steel deck and the concrete slab. And what that means is that we've basically created a reinforced deck almost for free. We're able to capitalize on steel's strength and tension to make it into sort of automatic reinforcing. The studs are necessary, again, to lock the cured concrete in place and to prevent the two from moving independently. So in summary, we have steel is part of this palette of materials that we have that we use very often when we need a lightweight structure, when we need it to be assembled quickly, and when typically we have a lot of repetitive parts in fairly regular geometries. It is generally more expensive than concrete, but generally quicker to assemble. We have a lot more versatility in terms of incorporating or integrating mechanical systems, especially if we use open web steel joists. And we're very often saving a little bit in terms of floor-to-floor height. Because steel is super strong, we get a little bit better depth to span performance out of it. We'll talk about one more structural material in the next set of lectures. Both a kind of ancient one and also one that is very new, very contemporary, and that is mass timber and cross-laminated timber. And as we'll see, it has some of the performance advantages of steel and concrete, disadvantages also on its own, right? And we'll talk about the ways that we balance decision making about which materials to use in various architectural types.